we're going to explore Gibbs free energy a little bit in this video, and in particular, its usefulness in determining whether a reaction is going to be spontaneous or not, which is super useful in chemistry and biology. And it was defined by Josiah Willard Gibbs. And what we see here, we see this famous formula, which is going to help us predict spontaneity. And it says that the change in Gibbs free energy is equal to the change in this H here is enthalpy. So this is the change in enthalpy, which you could view as heat content, especially because this formula applies if we're dealing with constant pressure and temperature. So that's a change in enthalpy minus temperature times change in entropy. Change in entropy. So S is entropy. And it seems like this bizarre formula that's hard to really understand, but as we'll see, it makes a lot of intuitive sense. Now Gibbs, Josiah Willard Gibbs, he defined this to think about, well, how much enthalpy is going to be useful for actually doing work? How much is free to do useful things? But in this video, we're going to think about it in the context of how we can use change in Gibbs free energy to predict whether a reaction is going to spontaneously happen, whether it's going to be spontaneous. And to get straight to the punchline, if delta G is less than 0, our reaction is going to be spontaneous. It's going to be spontaneous. It's going to happen, assuming the things are able to interact in the right way. It's going to be spontaneous. Now, let's think a little bit about why that makes sense. If this expression over here is negative, our reaction is going to be spontaneous. So let's think about all of the different scenarios. So in this scenario over here, if our change in enthalpy is less than 0 and our entropy increases, our enthalpy decreases. So this means we're going to release energy here. We're going to release enthalpy. And you could think about this as, so let's see, we're going to release energy. So release. So I'll just write, this is a release of enthalpy over here. I end up with less enthalpy than I started with, but entropy increases, disorder increases, the number of states that my system can take on increases. Well, this makes a lot of sense. This makes a lot of sense that this is going to happen spontaneously regardless of what the temperature is. I have these two molecules. They are about to bump into each other. And when they get close to each other, their electrons maybe say, hey, wait, there's a better configuration here where we can go into lower energy states, where we can release energy. And in doing so, these different constituents can part ways. And so you actually have more constituents. They've parted ways. You've had energy released. Entropy increases. It makes a lot of sense that this is a natural thing that would actually occur. So this over here, this is spontaneous. Delta G is not just delta G is less than 0. So this one over here, I'm going to make all the spontaneous ones. I'm going to square them off in this green color. Now what about this one down here? This one down here, delta H is greater than 0. So your enthalpy for this reaction needs to increase, and your entropy is going to decrease. So that's, you can imagine these two atoms or maybe these molecules, they get close to each other, but their electrons say, hey, no, in order for us to bond, we would have to get to a higher energy state. We would require some energy, and the disorder is going to go down. This isn't going to happen. And so, of course, and this is a combination. If delta H is greater than 0, and if this is less than 0, then this entire term is going to be positive, and so delta G is going to be greater than 0. So here, delta G is going to be greater than 0, and hopefully it makes some intuitive sense that this is not going to be spontaneous. So this one does not happen. Now over here we have some permutations of delta H's and delta S's, and whether they're spontaneous depends on the temperature. So over here, if we're dealing, our delta H is less than 0, so we're going to have a release of energy here, but our entropy decreases. What's going to happen? Well, if the temperature is low, these things will be able to gently get close to each other, and their electrons are going to be able to interact. Maybe they get to a lower energy state, and they can release energy. And they're releasing energy, and the electrons will spontaneously do this, but the entropy has gone down. But this can actually happen because the temperature here is low. And some of you might be saying, wait, doesn't that violate the second law of thermodynamics? And you have to remember, the entropy, if you're just thinking about this part of the system, yes, that goes down, but you have heat being released, and that heat is going to add entropy to the rest of the system. So still, the second law of thermodynamics holds, the entropy in the universe is going to increase because of this released heat. But if you just look at the constituents here, the entropy went down. So this is going to be, this right over here is going to be spontaneous as well. And we always want to go back to the formula. If this is negative and this is negative, well, this is going to be a positive term, but if t is low enough, this term isn't going to matter. T is, you can view it as the weighting factor on entropy. So if t is low, the entropy doesn't matter as much. Then enthalpy really takes over. So in this situation, delta G, we're assuming t is low enough to make delta G delta G negative, and this is going to be spontaneous. Now, if you took that same scenario, but you had a high temperature, well, now you have these same two molecules. Let's say that these are the molecules. Maybe this one's the purple one right over here. You have the same two molecules here. Hey, they could get to a more kind of they could release energy, but over here you're saying, well, look, they could, and the change in enthalpy is negative, but they're buzzing past each other so fast that they're not going to have a chance. Their electrons aren't going to have a chance to actually interact in the right way for the reaction to actually go on. And so this is a situation where it won't be spontaneous because they're just going to buzz past each other. They're not going to have a chance to interact properly. And so you can imagine if t is high, this term is going to matter a lot. And so the fact that entropy is negative is going to make this whole thing positive, and this is going to be more positive than this is going to be negative. And so this is a situation where our delta G is greater than 0. So once again, not spontaneous. And everything I'm doing is just to get an intuition for why this formula for Gibbs free energy makes sense. And remember, this is true under constant pressure and temperature, but it's those are reasonable assumptions if we're dealing with things in a test tube, or if we're dealing with a lot of biological systems. Now let's go over here. So our change in enthalpy is positive, and our entropy would increase if these react, but our temperature is low. So if these reacted, maybe they would bust apart and do something. They would do something like this, but they're not going to do that, because when these things bump into each other, they're like, hey, all of our electrons are nice. They're nice little stable configurations here. I don't see any reason to react. Even though if we did react, we were able to increase the entropy. Hey, no reason to react here. And if you look at these different variables, if this is positive, even if this is positive, as t is low, this isn't going to be able to overwhelm that. And so you have a delta G that is greater than 0, not spontaneous. But if you took the same scenario and you said, okay, let's up the temperature here, let's up the average kinetic energy, then these things are going to be able to slam into each other. And even though the electrons would essentially require some energy to get to really form these bonds, this can happen because you have all of this disorder being created. You have these more states, and it's less likely to go the other way because, well, what are the odds of these things just getting together in the exact right configuration to get back into this lower number of molecules? And once again, you look at these variables here. Even if delta H is greater than 0, even if this is positive, if delta S is greater than 0 and T is high, this thing is going to become, especially with the negative sign here, this is going to overwhelm the enthalpy and the change in enthalpy and make the whole expression negative. So over here, delta G is going to be less than 0, and this is going to be spontaneous. So hopefully this gives you some intuition for the formula for Gibbs free energy. And once again, you have to caveat it. It assumes constant pressure and temperature. But it is useful for thinking about whether a reaction is spontaneous. And as you look at biological or chemical systems, you'll see the delta G's for the reactions. And so you'll say, oh, it's a negative delta G. That's going to be a spontaneous reaction. It's a 0 delta G. Hey, that's going to be an equilibrium. Or you could say, okay, it's a positive delta G. That's not going to be spontaneous.